So in this section, we're going to talk about specifically heat in terms of changes of state. In case you don't know what that means, changes of state refers back to chapter 13 when we talked about physical changes. So in the first section, we talked about heat in general. The second section was more chemical, and then this is more physical changes overall. So physical changes in this video. So we can talk about what happens in general as we change from states of matter. So we got solid to liquid to gas, and if you think about the particles that make them up, you can think about whether or not they need to gain or lose energy to become a different form. Remember, solids are very uniform in their structure, very close together. So to get to a liquid where they're a little farther apart, enabled enough to slide past each other, a little more space, they would have to gain energy, and to become a gas farther apart with more energy. So in other words, as I travel this direction here, I find that this process as a whole is endothermic. In other words, they have to gain energy to transition from solid to liquid, liquid to gas. And we know those state changes for solid to liquids called melting. And then the liquid to gas change is vaporization. So we talked about in section 2 what it means to be endothermic in terms of enthalpy. We would say that since this is endothermic, the delta H or enthalpy for any of these processes, melting or vaporization, should be a positive value. Now if you look at the reverse of this, go the opposite direction, the reverse processes, the opposite of vaporization going from gas to liquid is condensation, and liquid to solid is called freezing. Now you're going to see some other names for some of these processes, but that's all we're talking about in this section. And since this is the opposite of what we saw above here, an endothermic, this is going to be an exothermic process. So this is exothermic. Sorry, that's squished in there. And because it's exothermic, we'll find that enthalpy given off is negative, or the enthalpy is negative, I should say, because energy has to be released as you go from something that's a gas, high energy. Energy must be lost to the surroundings so they can get closer together and move a little bit slower, and the same process happens for freezing. So overall, we're just understanding that as you go from solid to gas, it's endothermic and you're gaining energy for the system, and the system is losing energy and it's exothermic if you're going from gas to liquid to solid. This picture here below is called a heating curve, and this is specifically for water. There's a couple of things that you might recognize. For example, this is ice, which we know is a solid. So we've got solid ice, and then liquid water. So this is our liquid, and this is our gas, which we call steam often. And it has a couple of things you'll recognize. At this point right here is where we find the transition between solid and liquid. So as we move this way, heat added left to right, heat added in time, going this direction as the arrow implies. This right here would be the melting point. And again, it would also be, if you're going the other direction, the freezing point. So notice this is in Kelvin over here. It doesn't say it, but it is in Kelvin. And this would be 0 Celsius or 273 Kelvin at this point right here. And then liquid to gas, up here we have this point. If you follow this across, that would be 100 degrees Celsius or 373 on the Kelvin scale overall. And that would be the boiling point and the condensation point overall. So this goes back to chapter 13 when we talked about the idea that if I have a hot plate, I got some water on that hot plate, and I've got this knob that controls how hot something is. So I've got this water in the hot plate, and I've got a thermometer sitting in the water there. That's a horrible thermometer, but you get the idea. This should say 100 degrees Celsius if it's boiling. But what if I were to crank the temperature, turn the knob even more? What would happen to the temperature of the water? And the answer is nothing. The temperature or the number on this should remain the same. And that's exactly what the heating curve shows. We're talking about this transition right here. As I take liquid water and it reaches its boiling point, 100 degrees Celsius, it will stay at that temperature. Notice this doesn't increase here, but there is energy or heat, a form of energy, added to the system over time. So you can see this line right here is a little bit longer than the line here. This means it requires more heat or energy to completely change all of my liquid water to a gas. Notice the temperature doesn't increase until I get to this point right here. And that's when all the molecules have changed from the liquid state to the gaseous state. So realize that steam can contain more energy than water can, because it will max out as far as temperature and kinetic energy goes, average kinetic energy, until it transitions into a gas. So on this diagram here, I'm going to clear this out and show you some other things. We can see the same thing we talked about above, the state changes we mentioned before. So again, this is solid, liquid, sorry. So we've got solid, liquid, gas, and those transitions we saw, this direction going that way, are the transitions of solid to liquid. Is called melting, so this is melting. The fancy name for this is the enthalpy, or energy needed for fusion or melting. And the process as you go from liquid to gas is called vaporization, so they call it the delta H of vaporization. So think about it again. What should these enthalpies be, positive or negative? Solid to gas, you need to add energy to these systems, so they should be endothermic or positive. And the reverse of this should be the same amount of energy. Notice the distance is the same, so the energy is the same, but the enthalpy change, in this case going from liquid to solid, and that's called freezing, or in this chapter they call it solidification. So solid, delta H solid, this would be a negative value, because you have to give off energy for this liquid to become a solid, to become more ordered. Up here, the delta H of condensation, C-O-N-D, is also going to be negative to give off energy. So this is just, again, a way that we relate energy in terms of state changes, and the realization in this section that energy is either given off or absorbed depending on the state change that's occurring. So this graphic shows the same thing that I was just showing on the heat curve, and we define some things. So molar heat of fusion is just a fancy way of talking about the amount of energy to melt. Again, fusion is melting 1 mole of a substance. Again, this process, like I mentioned, is endothermic, and you can see over here on the graphic the fusion as I go from solid to liquid to gas. All of these phase changes require energy into the system, and so they are all positive values here. Going the opposite direction, solidification or freezing, notice solidification is freezing, same thing. This is the opposite process of fusion or melting. And so in this case it's exothermic, again restating what we said a second ago. So this molar heat of solidification is a fancy way of saying the amount of energy needed to change 1 mole of something from a liquid to solid. So we can start seeing this relationship that if you have opposite state changes, in other words, melting, freezing, or fusion, the fancy way of saying melting, and solidification, the fancy way of saying freezing, the amount of energy needed to make those transitions is the same, but how that energy is absorbed or released is different. So we have to show that with this sign. This would be a positive sign here, and the sign for solid would be negative, because this is losing energy, this is gaining energy for it to melt into a liquid. So you can see in these equations, they're not chemical equations but physical change equations, solid to liquid or melting, this heat of fusion is 6.01 kilojoules per mole for 1 mole. The opposite process, liquid to solid or freezing, is the same number, but it is negative rather than positive. So I can use these numbers like I did in section 2 to figure out how to get to energyville, or energy, given a mole or gram value. So in this example here, we have a popsicle, but really it's an icicle, because it says how many kilojoules of heat are required to melt 10 grams, a 10-gram popsicle at 0 degrees Celsius. Assume the popsicle has the same molar mass and heat of fusion as water. So I'm going to start out with 10.0 grams of water. That's what we're talking about. It's really a popsicle, but we said it has the same molar mass and heat of fusion as water. Now 0 degrees just tells me that this is solid, and we're talking about melting it. So it's going from solid to liquid, which looks like this information right here. So the first step is to go from massville to moleville, grams of H2O to moles, of H2O. 1 mole is equal to 18.0 grams. This is old stuff. Grams are now gone. Next step is to go from moles of H2O to my kilojoules. This is the new road we've been traveling. In this section, we're talking about the relationship between moles and the energy needed to change state. In this particular instance, we're using this information that was given to me. I didn't have to calculate anything. I just have to know that this says for every 1 mole, I am going to absorb 6.01 kilojoules of energy. And if you do the math on this, it should be 3.34 kilojoules of energy required to melt the 10 grams of ice, essentially. We also see that there are enthalpy values for other state changes too. So for example, vaporization going from liquid to gas, and the molar heat of condensation going from gas to liquid. They are equal in number, 40.7, but opposite in charge because this is an endothermic process, so it's a positive number, and this is an exothermic process, giving off energy as it transitions from gas to liquid. If you have the notes and you're watching this, notice that these values should be changed or highlighted because they were a fusion originally, and they should be vaporization and condensation. So this is the same idea. Again, if you're given these values and you're talking about steam, gaseous water, or liquid water, you now have the numbers needed to figure out any energy versus mole, gram conversions you might see. So in this case, it says we have 63.7 grams of water in the liquid state, so we could write that down if we wanted to. And they want to know how much heat is absorbed. Absorbed is a key. This is going to be endo. And it also talks about being converted to steam. So we're going from liquid to gas. So this all makes sense. This is a positive number. It's endothermic, liquid to gas. So this is the information I'm going to need in that last step. So like in the previous example, I want to go from grams of water, which is 18.0 grams of water, to moles of water. Then convert the moles of water at that point. This is the new thing, moles of H2O, to kilojoules. So it says in this information up here, because I'm going through vaporization, that I would want 1 mole right here, per 40.7 kilojoules. So 63.7 times 40.7 divided by 18 should give you a grand total of 144 if you use sig figs. And that's kilojoules. These cancel out. That's the amount of energy you would need. So this is not a whole lot different from what we saw with chemical reactions. We're given a delta H, and it's telling us if it's exo or endothermic. We're just dealing with state changes. The last idea in this video is we're going to talk about a state change where things get dissolved. So we have this molar heat of solution. When you take a solid and dissolve it in water, there isn't a change in the heat content of the system. And we symbolize that with delta H, the enthalpy of SOLN, solution. So for an example, we can make a little equation. It's not chemical, but show that NaOH dissolves in water and becomes its ions, Na plus and OH minus. When it does this, in particular this substance, it will, as you can see from the delta H of solution, give off energy, specifically negative 445 kilojoules, 0.1 kilojoules, or 445.1 kilojoules. Doesn't mean negative, we're giving it off, that's what it tells us, per 1 mole of sodium hydroxide. So using that information, I could also, if given a question about dissolving something, which this is talking about, calculate energy. So really there's no difference among all these problems we've done in section 2 and 3. We're using this delta H value to convert between moles and the energy related to that amount of substance. So in this question here, we have 0.677 moles, so we don't have to go from Massville. We could start out there, but we're not in this question, of NaOH. And they want to know how much energy is released from that amount of moles. So I want to get rid of moles of NaOH. And again, I'm going to use this information that says that 1 mole of NaOH is going to release negative 445.1 kilojoules. So again, since this is releasing energy, we would expect our number to be negative, which it should be based on the way we set up our equation. So 0.677 times 445.1, or negative 445.1, gives you 301, negative 301 kilojoules of energy.